Hello students, welcome to my channel Maths with Panu. Today I am discussing with you the topic of Fourier series. In my first video, I had told you the basic of the Fourier series. Now in this part we discuss its even and odd functions, its half range, sine and cosine series. So let's start. First of all, we see the definition of even function. If fx is an even function in a Fourier series, then we take Bn is equal to 0. For this series, if we are given the interval minus L to L, then we apply the formula of A naught and An. We need not find the value of Bn. We write here A naught is equal to 2 by L sine of integration, and we take the limit 0 to L fx dx. And if we find the value of An, then we take 2 by L sine of integration. We take the limit 0 to L fx cos n pi x over L dx. In the second part, if fx is an odd function, then we need not find the value of A naught and An. Means A naught and An is 0 in this part, and we find the value of only Bn. And the formula of Bn is 2 by L sine of integration and the limits 0 to L fx sine n pi x over L into dx. To prove our definitions, we take an example. If we take the function fx is equal to x square, and here the interval is minus 3 to 3. So, in this question, we have our limits L is equal to 3 here. We write here fx is equal to x square. Now, if we want to find fx is an even function or not, then we apply this formula. We put minus x in the place of x in our function, and we put on the right side also. After solving it, we get the same function. Means if f of minus x is equal to fx, then fx is an even function. Or if we put minus x in place of x and we get minus fx, if we here get minus fx, then fx is an odd function. But in this question, we take fx is an even function. For this, we apply our above formula and Bn is equal to 0. So, we find our Fourier series for this interval. Fx is equal to A naught upon 2 plus summation n from 1 to infinity An cos n pi x over 3. We can name it as a equation star. Now we put these values. We write here fx is equal to 2 upon 3. 3 is L. We put 3 in place of L. So we write here 3, taking the limit 0 to 3 x square dx, and we take the integration and we apply the formula x to the power n is equal to n plus 1, x to the power n plus 1 upon n plus 1. After that, we write here our upper limit minus lower limit. After solving it, we get our answer 6. Now, we move on our next Fourier coefficient, that is an. So, we write here again by formula 2 by L. Here L is 3. Taking the sign of integration 0 to 3 x square cos n pi x over L. Now we apply our chain rule as we done in our previous example. So we take x square our first function and cos n pi x upon 3 our second function by the formula of I late. So we apply the chain rule now. We take first function as it is, integration of second, the derivative of first, double integration of second, double derivative of first, triple integration of second, and so on. Now we apply x, we write x square as it is, integration of cos is equal to sine. We write here sine n pi x upon 3 and coefficient of x is n pi upon 3. We write here, we write it in the denominator. After that, by the formula, we take the derivative of x square. Then we apply the derivative of x square is 2x here, and integration of sine is minus cos n pi x upon 3, and we write the coefficient of x n pi upon 3. You can see here we have already our first coefficient n pi upon 3, and if we take the integration on second time, then we again write this coefficient in the denominator, then we get n pi upon 3 to the square. And in the third step, we again take the derivative of 2x is 2 and the integration of cos is sine, and we get n pi upon 3 to the cube in the denominator. Now, in the next step, you can see here we put the limits. After that, you put here upper limit minus lower limit. You put 3 in the place of x. First of all, we put 3 the square, sine n pi 3 upon 3, and so on. In the place of x, you put 3 in your first part. Then apply minus sign and put 0 in the place of x in your second part, but you need not try to write here, because when we put 0 in the place of x, then you can see this part will be 0, and if we put here in the 0 in the place of x, then you get 0, and you know that sine n pi 0 is also 0. Now, in the first part, you get sine n pi. If n is any natural number, means if n is 1, 2, 3 and so on, then we know that sine n pi is 0. The value of sine n pi may be sine pi, 2 pi, 3 pi, 4 pi, for any n for any natural number, we have the value of sine n pi is 0. So, the first and the third term is 0. Now, we see our second term, 2 3s are 6, n pi to the whole square 3 to the square 9, and minus cos n pi 3. Cancelling 3 from the numerator and denominator, you get only cos n pi. Here, the value of the cos n pi is minus 1 to the power n. I repeat, the value of cos n pi is minus 1 to the power n. Now we put these values in our equation star. Put the value of a naught upon 2 and you write here the value of an and you get your Fourier coefficient. Now we move on our third part of the Fourier series, that is half range cosine and sine series. Before taking an example, I want to clear the definition of half range cosine and sine series. So students, we can take two types of interval. In the first part, if we take the interval 0 to L, here you can see 0 to L, then we write our cosine series in this way, a naught upon 2 plus summation an cos n pi x upon L, where the Fourier coefficient a naught is equal to 2 by L limit 0 to L fx dx, and the Fourier coefficient an is 2 by L 0 to L fx cos n pi x upon L. And if we take our sine series, then we write here fx is equal to summation bn sin nx, and the value of bn is this. Here we use L, only L, 0 to L. Here L is constant term and we write here sin n pi x upon L, not pi. If you want to take pi, then you can see in your second part, if we take the interval 0 to pi, then we write here fx a naught upon 2 plus summation an cos nx, and we write here 2 by pi limit 0 to pi in the place of L. We write L in our first type and we write pi in our second type. So you write here pi if you are given the interval pi, and you write L if you are given that interval. Then in the same way you can write fx bn sin nx, and bn is 2 by pi 0 to pi fx sin nx dx. You can observe that we write here cos nx, and in our previous formula we write here cos n pi x upon L. That is the basic difference. Here we write L, and in the second part we need not to write pi in the denominator. So you can see that in half range cosine series, when you find the value of cosine series, you need not to find bn here. You only find a naught and an. And if you find the value of half range sine series, so you apply only bn. You need not to apply an. Here a naught, you only find the value of bn. We take an easiest example to prove our concept. So we take an example, fx is equal to 1 and we take the limit from 0 to 2. 2 is working here in the place of L. So first we find Fourier cosine series for our function L is 2, and we apply our Fourier cosine series. You can see here we firstly find a naught, you apply 2 by L. L is 2 here, and you write fx is equal to 1. The integration of 1 is x, cancelling 2 you get only x, and after that you put upper limit minus lower limit and you get the answer 2. After that, we find the value of an and we write here fx is equal to 1. We all know that the integration of cos is sine n pi x upon 2 and the coefficient of x is n pi upon 2. Then we write here upper limit minus lower limit. N pi by 2 you can take it in the numerator. You can write here 2 by n pi. And then you apply upper limit minus lower limit, and we know that after cancelling 2 we get only sin n pi. The value of sin n pi is 0 and the value of sin 0 is also 0. Okay, and you get the value of an is equal to 0. Now your Fourier cosine series, you put the value of a naught and an in your cosine series, and you notice that the value of an is 0. So we have no R series because we cannot put the value of n, 1, 2, 3 and so on. So we have only a constant, that is 1. So there is no cosine series. Now we move on our Fourier sine series. You can see here we write the Fourier formula for Bn and we write 2 by L, 0 to L, fx is equal to 1, sin n pi x, L here is 2. Again, after cancelling 2 you get only sine function. Integration of sine is minus cos n pi x upon 2. After putting the limits, you get cos n pi minus 1 because cos 0 is 1 and the value of cos n pi is equal to minus 1 to the power n. I repeat, the value of cos n pi is equal to minus 1 to the power n, and if you take the sign minus within the braces, then you take 1 as your first term and minus 1 to the power n is your second term. Now half range Fourier sine series is fx is equal to summation bn sin n pi x upon 2. You put the value of the function and the value of bn. So this is your half range sine Fourier series. Thank you so much.